Okay, so we're going to continue. So recall that last time we were talking about intersection numbers. So we said, if we have a function, our setup was we had manifolds x, y, and w, where w was a subset, submanifold of y, which was closed, and x was compact, and none of them had boundaries. And then we also had the dimension condition. So if the dimension of x plus the dimension of w equals the dimension of y, and we said, well, if f is transverse to w, then we can define the index, the intersection number, of f with respect to w, which is basically the number, the signed count of points in the preimage of w. Okay? And then at the end of the class, we said that even if f does not intersect w transversely, so for any f, a smooth function, we can still define the intersection number by just looking at a perturbation of f. I mean, actually anything that's homotopic, but in particular, you can take a perturbation. So that was our definition. And we proved that if two things are homotopic, then their intersection numbers are the same. So that means that this definition is good. It doesn't depend on which representative, which f tilde you pick. Okay? So that's very nice. And we can talk about intersection numbers in more general contexts, but you have to be just a little careful. Like, for example, it's possible to talk about it when x, y, or w have boundary, but you have to be a little bit careful because then things stop being invariant sometimes. If you can go through the boundary, then you might lose this count. So, but if you know what you're talking about, then you can actually talk about intersection numbers in more general cases. So, for example, I guess something that comes up in an example of something different, but I think it's still kind of nice, is in knot theory. So when you're starting knots, knot theory is basically the study of embeddings of S1 into R3. So an embedding of S1 into R3 is called a knot. So, we kind of have a trivial embedding, which is, what's called the unknot. And then you have more complicated embeddings, like you have the trefoil. That's the second easiest embedding. And then you have other embeddings, the figure 8 knot, and I'm not going to draw very many, especially on this tablet, but you have many knots. And there are many. Knot theory is actually an active area of research, and there are very hard questions, but one of the simplest things in knot theory is called the linking number. So given a knot, you can always orient it. So, say I have my trefoil and I can orient it. Let me take my trefoil here. It's not the most beautiful trefoil, but it's a trefoil. You can orient it. So, just think of an orientation of S1, which will induce an orientation of the knot. And if you take another knot, say, now I take hold on. So say I take this other knot. Then there's something called the linking number, which basically is telling you how many times the two knots are connected. If you just have the linking number if the linking number is 0, that means that you can disconnect the two knots and they're not, you can put them in separate neighborhoods. But the linking number is a very interesting invariant. So, I mean, you might or might not have seen the definition of the linking number, but I can kind of tell you what it is. So what is the linking number of K and L. Well, you can think of the knot, when I draw this picture, I really am thinking about the projection of this picture to R2, or you can look at this picture and you can imagine what the knot embedded in R3 is. But what's the linking number? The linking number is basically, you look at every intersection of the projection of K and L, and so if this is K and this is L, you look at how they intersect, all the intersection points, and you just count them. But then you have to put signs. So if they intersect like this, with one of them, with this one on top and this one in the bottom, you say this is a plus. And if they intersect like this, you say this is a minus. So you have to count the number of intersections, or I guess the number of intersections of the projections, and with the signs, and then you divide by 2. Okay, so you can kind of see that it's always going to have, this number is always going to be even. So you have to divide this by 2. I mean, you don't have to, but you do divide it by 2. Okay, so that's what the linking number is. And you might wonder, why am I even talking about linking number in this class about intersection theory? And the reason is because there is a way to compute linking numbers, or even to define linking numbers if you want, that has to do with intersections. Because here, it's not, it's a little bit funny what I mean by intersections here, because actually I'm looking at intersections in this form, and it's not clear really what's going, this is not exactly the intersection theory that I was talking about, because when you project it to the plane, the intersection number is always going to be 0. So it's some other intersection. And in fact, what it is the following thing. So given a knot, there is something called a ciphered surface, which is a surface embedded into R3, which is oriented. So it's an oriented surface, and whose boundary is equal to K. So you take an oriented knot, and then there exists this surface called the ciphered surface, and it will, and that has this property. And then the linking number of K and L, you can think of this, or I guess by one of the definitions, or you can prove using this definition, is that this is the intersection number between S and L. And then, here you might be like, wait, you said that both things had to have non-empty empty boundary. So how can you do this with S? And that's why, you have to be a little careful. It's the intersection number, but here, you only allow homotopies that don't cross the boundary. So you could do this kind of thing. You can be a little bit more subtle about how you're defining what kinds of conditions you put. And in the particular, you could compute the intersection number between a manifold with boundary and a manifold without boundary. And even two manifolds with boundary, but you just have to be extremely careful about which conditions you put. Okay? So, yeah, and actually, if you believe the ciphered surface exists, then it's not so hard to see this, because if this is your knot K, and then here's your ciphered surface, and it's oriented so that K is the boundary of S, then basically it means, it's oriented this way. So when you have another knot, if it comes over, then it's going to intersect the surface negatively, and if it comes under, then it's going to intersect the surface positively. So you can kind of see this just from here. You can see these signs from here, and you have to see that to actually go do a whole you actually are going to have another intersection later, but at least to see the signs, you can see it from here. But anyway, this is not in the scope of this course, but I just wanted to tell you how this appears in other contexts. Okay, so any questions about this? I know it's kind of a tangent. Well, it's actually a very interesting little construction that's due to Ciphered, how to construct a surface. that bounds the knot that's embedded. And I mean, I guess if you've never seen this, it's maybe kind of surprising, but it's not very hard. You know, basically, you just have to look at the projection of the knot, and you have to get rid of these crossings and smoothen it, and then get a surface or something that will be bounded by this projection. And then every time you have a crossing, you have to do a twist. So yeah, for example, I guess a nice example is this thing here is also the trefoil, but it's another way to see the trefoil. And it's not very hard to see that this surface here, S, bounds the trefoil with the right orientation and is an orientable surface. So yeah, so that's such a surface. And it's actually slightly subtle, because if you looked at the original trefoil that I showed you, this original picture, and you say, well, let me do something even easier, which is just consider this surface here. This surface is actually a Möbius band. It's non-orientable. So this is not a Ciphered surface. But this one is a Ciphered surface. Okay? So it's not completely obvious that every knot has a Ciphered surface, and the construction that I mentioned to you, you could apply it here and you will not get this Möbius band. You get something a little more complicated. But it's going to be exactly the same as this. Okay, so that was a kind of a long tangent, but I still wanted to say that. Yeah, so I guess the point is that sometimes you want to consider intersection numbers that are not between two closed surfaces, and you have to be a little more subtle. But if you know anything about algebraic topology, that's similar to when you look at intersection numbers of where one of the classes is in a manifold relative to it is in the homology that's relative to the boundary. Because if you look, if the manifold has boundary, then the homology, the total homology, will be 0. So intersection numbers will not be well defined. But if you look at the surface, the manifold with boundary, and you look at the homology relative to the boundary, then it's no longer going to be 0 in general. So anyway, that was kind of a tangent. Okay, so let's go back to what we had. So we had defined intersection numbers for, so we had our x, y, w with the conditions before, and then we had a function, a smooth function from x to w, from x to y, and then we defined the intersection number of f and w. Okay, and we can do lots of things with it, but now I want to talk about degrees a little bit. So the degree is a specific kind of intersection number. I want to talk about degrees. So the degree, the setting is the following. So x and y are oriented manifolds without boundary. X is compact. And for things to really be well defined, I'm going to suppose that y is connected. And the main thing here is that the dimension of x is equal to the dimension of y. So it's basically, now we want to do intersection theory where w is a point. So then we can define what's called the degree. So if f is a function c infinity of xy, we define the degree of f to be the intersection of f with a point y, where y is some point in capital Y. Okay, so this is just a particular case of the index, but it's going to be something that appears a lot, the degree. Okay, So for the degree to be well defined, we need the two manifolds to be oriented, to have with no boundary, and for X to be compact and for Y to be connected. Okay, and the most important thing is they have to have the same dimension. Okay, so we have to see that this is well defined. So what do you need to show that this is well defined? Well, you need to show that this guy here does not depend on Y. So proposition, this intersection number doesn't depend on Y. Okay, so this is where we actually are going to use the fact that the manifold Y is connected. Otherwise, it depends on the connected component. Okay, so how do you prove that? So first of all, we can assume without loss of generality that F is transverse to Y. So we may assume without loss of generality that F is transverse to Y. In other words, that Y is a regular value for F. And that's just because of the Thom transversality theorem. If it's not, then you can perturb it a little bit to something homotopic that will be transverse to Y. Okay? So, that means that Y is a regular value of F. So now, the preimage of Y, because X and Y have the same dimension, the preimage of Y is going to be a collection of points. It's a finite number of points. Finite set. Okay, and and now if you look at now I'm going to choose little neighborhoods around these points. So let U1 through UK be small neighborhoods of X1 through XK. And since each of these points, since Xi is a regular point, by the inverse function theorem, this F has to be a local diffeomorphism if Ui is sufficiently small. F restricted to Ui is a local diffeomorphism if Ui is sufficiently small. Okay, so we choose these UIs small enough so that F restricted to them are local diffeomorphisms. Okay. And the other thing to notice is that the derivative of the function df at the point xi, because xi is a regular value, then it maps the whole tangent space to ty of y. Okay. So now, basically, this xi also comes with a sign because because the manifolds x and y are oriented, and the sign of this xi is going to be +1 if and only if the orientations here match. So if and only if the orientations above match. Okay, so basically, if and only if df xi preserves the orientation. So it's orientation preserving. So the sign is going to be -1 if dfi is orientation reverse. Okay, so now we're really going to use the inverse function theorem in the following way. So by the inverse function theorem, basically you can always choose charts so that by the inverse function theorem, we for each I, or around each around each xi, we can choose, no, for each xi, we can choose charts around xi and y, so such that, so I can choose a chart. So here's my f, here's xi, here's y, so I can choose a chart here, phi, and I can choose a chart here, psi, and I can just choose one chart for everyone, such that when you look at psi composed with f composed with phi inverse, you basically get the identity map, at least in the neighborhood. So this is a map from Rn to Rn, and we can choose it so that this is the identity. Okay, that's because of the inverse function theorem. But now you actually have to be a little careful, because basically, you know, what I would like to say is, I would like to say that this map here is, I don't actually need it to be the identity, but I want it to be orientation preserving. Because I want it to kind of encompass, I want to look at this guy and to see what's happening just from Rn to Rn. So basically, I can either, this map, if I want this whole thing to be orientation preserving, then depending on whether f is orientation preserving or orientation reversing, I actually don't, this doesn't have to be the identity, because, you know, to make it the identity, I might have to switch the orientation somewhere. So if I want the orientation to be preserved, then I can always make it either the identity or a fixed map that that has degree that changes the sign, where the sign is -1. That's orientation reversing. So for example, the reflection, a reflection. So either this one or this one. So so again, you know, let me say one more time. The inverse function theorem will tell me, you know, that because this map is a local diffeomorphism, the derivative here is a bijection, I can always choose two charts to make it the identity. But then one of these charts could actually be switching the orientation of Rn. Or, you know, I can take a specific chart with a specific orientation, but I might have to switch the orientation of Rn. I might have to take something where the determinant is negative. So I don't want that. So I want to always have things with a positive determinant. Yeah, so basically sorry, what I mean to say is that I want the charts to be orientation preserving. So I want the two charts to be orientation preserving, which means that there's no way that in general, if df reverses the orientation, if it doesn't preserve the orientation, then I'm not going to be able to get to the identity. I'm going to get the reflection, because the composition of orientation preserving is orientation preserving. So this is a little fact that you can check, that, you know, any orientation reversing map from Rn to Rn, you can, if it's or any linear transformation that's orientation reversing, you know, up to a homotopy, it can be homotopy to a reflection. Okay, so anyway, so it's either the identity or the reflection, and then this, what this is saying is, like, basically it's going to be the identity if and only if dfxi preserves the orientation. But the point is that it's the identity everywhere in this neighborhood, not just in xi. So this is going to be, you know, the identity if and only if dfx preserves the orientation for every x in ui. So, you know, this whole argument is to say that the sign of this point will not change. So basically, you know, if I have my xi and I have my diffeomorphism f to some v, so here's my ui and here's v. The point is, if I choose another point, if I move my y here, so if I choose another point in the neighborhood of this original y, I'm going to have a unique image here. And by this argument over here, they have the same sign. The sign of xi is equal to the sign of xi tilde. So the conclusion is that for every y tilde in V, so this is an open neighborhood of the original y, the pre-image consists of exactly the same number of points, k points, such that xi tilde is in the original, in ui, a small enough neighborhood around xi, and the sign of xi tilde is equal to the sign of xi. Okay? So that is saying that I of f y, that this intersection number is locally constant. So if you vary y in a small enough neighborhood, this number doesn't change. Okay? So it's a function. You can think of this as a function from y to z, which is locally constant. So that means that because y is connected, then this has to be constant. Since y is connected, this function is constant. Okay? So that's the end. So this is the proof that the degree is well defined. Okay. Are there any questions about this?
Professor,
Oi.
Quando você toma para a imagem do y-til, tipo,
Sim.
só tem K ou podia ter tipo, mais dois com sinais trocados?
Não, tem exatamente K. There is exactly K because you're assuming that y is a regular value. So since y is a regular value, then the preimage of y, each point of the preimage of y is a regular point. So f is a local diffeomorphism near that point. So if you start with a y that's not a regular value, then it is true that in the image, in a neighborhood, other things could happen. But first we homotope f so that we don't have this problem. So we kind of change the f so that y becomes a regular value. Okay, so let me give you an example. I think the example might shed light into it, which is a very simple example, but very important. The example is a function that goes from S1 to S1 that is given by z to the n. So this is when you think of S1 as a subset of C. Okay, so you take your complex number and you take the nth power of it. Okay, so this is interesting. Actually, hold on. No, okay. This is not. This is also interesting, but it's not going to tell the answer of what you want to see. But let's start with this one. So first of all, you see that the derivative here for a point z, this is tz of s1 into tz of s1, and you can think of this as like the real line, and this is the real line, and the derivative is just going to be multiplication by n. Okay, so I guess it's just nz, nx. Okay, so if n is different from 0, then this dfz is different from 0. So every y is a regular value. And then the preimage of y is going to be n points. Actually, like this, because n could be negative. Okay, and the point that you can check is that basically the sign of the point, the sign of xi is the same as the sign of the number n. So if n is bigger than 0, then the sign of xi is going to be +1, and if n is less than 0, then the sign of xi is -1. I guess it's not so hard to see here. Like this identification, the df is just multiplication by n. So if n is positive, then your multiplication by n is a isomorphism of R that preserves the orientation. If n is negative, it changes the orientation. So these are the signs. And then finally, so that means, and if n equals 0, I guess that's an interesting case. I mean, it's kind of like what you asked Marcelo, but it's the easiest possible case. So if n is 0, then this function is constant. Then the function f of z is just always equal to 1. Which means that, and of course, df z is equal to 0. So that means that 1 is a critical value. But any other point, but if I take y, which is different from 1, then y is not in the image, so y is a regular value. And the preimage of y is empty. So, in this case, the degree of this this f is going to be 0. And you can see the other cases, basically for every case, the degree, if f is just z to the n, then the degree of f is always going to be exactly n. So, like if n is greater than 0, then you have n points all with sign +1, so it's n. If n is less than 0, then you have absolute value of n points, all with degree -1, so you have the degree n. And in the case n equals 0, you also have the degree 0, so the degree is n. So this is the general fact. Okay. Okay, so that's interesting. Let me say one more thing, which is that if x is, for example, is the boundary of any ball of radius r, it doesn't even have to be, it doesn't have to be the unit ball. Then, and we can consider the function that's very similar to this, but just taking x divided by r, or z to the n divided by r, then again the degree of f is equal to n. Okay, so this is something that we're going to use in a little bit. But before I go into proving the fundamental theorem of algebra, which is the next thing I'm going to do, I want to try to answer Marcelo's question again. So if you take the same function z to the n, you can think of it as a function first from c to c that takes z to the n. And now you can compactify this function, and you get a function f tilde that goes from S2 to S2. So you can think of C as C union the point at infinity. You can think of that as S2. So it's not very hard to see that you can actually extend this function to a smooth function from S2 to S2. And now you can ask about the degree of this function. So now you can ask about the degree of this f tilde. And it's not very surprising, it's actually it's the same calculation. You have to be a little more careful because now your function, your manifold has dimension 2, but it's pretty much the same calculation. The derivative is slightly more complicated, but it's pretty much the same calculation here. And you conclude, if you take a regular point, so if you take a point in S2, which is neither 0 nor infinity, then y is a regular value. And the preimage of y is a bunch of points. Okay, that's, because here, every point is going to have exactly n preimages unless it's 0 and infinity 2. And you can check that the sign is the same. So again, basically, this tells you that the intersection number of f tilde and y is going to be n. And here, I guess you can see what what Marcelo was asking, which is, think about this map from C to C that is just z to the n. So here's my origin, and I take z to the n. So when I pick a point here that's a regular value, that's away from 0, then it's going to have exactly n preimages. And if I change it a little bit, if I wobble it around, I'm going to still have exactly n preimages. But if I take a point that's a critical value, then the preimage of that, in this case, is just 1 point. It could be more than 1, and what happens here is that that number of preimages is not locally constant when you take a critical value. I think that's what Marcelo was asking about. But that doesn't actually come up in the proof of what we had, because for the proof, you really only need to consider regular values. Otherwise, you perturb the function. And then you have whichever point you had becomes a regular value for the new function. Okay? So, anyway, is that clear? Marcelo, entendeu?
Aham.
Beleza. All right. So, other questions? Other questions? No? Okay, so now I want to prove the fundamental theorem of algebra. Okay, so let P be a polynomial complex polynomial of degree n greater than or equal to 0, then P of z has a root. In other words, there exists some z in C such that P of z is equal to 0. Okay, so you see that you can prove this. I mean, if you know fundamental group, this you can prove that with a fundamental group, but we can prove this with degree theory too. And in the case, for circles. So let me write the polynomial like this. So let P of z be an z to the n, or actually, I can just divide by an. So I have z to the n plus an minus 1, z to the n minus 1, plus etc., plus r0. And then I can consider an r, which is sufficiently big, such that r to the n is greater than the absolute value of an minus 1 times zn minus 1 times rn minus 1 plus etc. plus the absolute value of a0. So you can always do that because this polynomial, has degree n. Like if you divide this one by this one, as r goes to infinity, this goes to infinity. So at some point, this quotient has to be greater than 1. So you can always find an r that satisfies, for which this is always satisfied. And then we are going to define a homotopy, pt of z, basically between the polynomial z to the n and the polynomial p. So I'm going to do z to the n plus t times an minus 1, z to the n minus 1, etc., plus a0. Okay, so this is a homotopy, a smooth homotopy. And you can check that if the norm of z is equal to r, then the absolute value of p of z is going to be equal to this guy, z to the n plus t, no, oops. And this is greater than or equal to the norm of z to the n, the absolute value of z to the n, minus t times the norm of an minus 1, norm of z to the n minus 1. This is the triangular inequality, minus norm of z 0, which by this condition here is going to be greater than 0 for every t between 0 and 1. So that means that pt of z does not have a root. On the circle of radius r. Okay, so then we can define a homotopy that I'm going to call ft, which is just pt over the norm of pt, and this goes from the boundary of the ball B0R to S1. Okay? And, you know, of course, yeah, F1 is equal to P1 over norm of P1, and F0 of z is just z to the n over r to the n. Okay, so now if P1, sorry, it's not P1, it's P. It's my original polynomial. So if P doesn't have a 0, then I can actually extend P over P over the norm of P to all of the disk. So if P doesn't have a 0, then P over norm of P extends to the whole B of 0R to S1, which will mean that the intersection number of F1 with 0, with any point, which is the degree of F1, is equal to 0 by that lemma. So if I can extend it to a manifold with boundary, then the degree has to be 0. Okay? But on the other hand, the degree of F0, we computed that this guy is not 0. In fact, this is n. So if n is different from 0, then we have a contradiction. So the conclusion is that P has a root. Okay? So anyway, that's a little bit of degree theory for you. I mean, I guess we used something that we didn't exactly state, but it's kind of obvious from the definition, which is, maybe I should say, I should write this as a proposition, but we don't need to prove it, which is that if you have f and g, which are functions from x to y, and dimension of x is equal to the dimension of y, x is compact, and y is connected, then the degree of f is equal to the degree of g. Okay, I mean, this, we kind of used it here, but it is obvious because it just follows from the, oh, I forgot to say the f, the most important condition, which is that f is homotopic to g. Okay, so it's obvious because we already know that the intersection number is invariant under homotopies if you fix the same submanifold. Okay, so anyway, this is the basic, you know, definitions of degree, and I guess the most very interesting theorem is the fundamental theorem of algebra. So now I want to state a theorem that we'll prove later, which is quite a beautiful theorem. It's called the Hopf theorem. So, you know, we know that by this proposition, we know that if you have two maps that have the same degree, the two maps that are homotopic, then they have to have the same degree. And then you can ask yourself, what if you have two maps that have the same degree? Do they have to be homotopic? And the answer is not necessarily, but sometimes they are. So the theorem, the Hopf theorem, says the following thing. So if f and g are maps from Sn to Sn, such that f is homotopic to g, no, sorry, I think that's enough. They just have to be maps from Sn to Sn. Then f is homotopic to g if and only if the degree of f is equal to the degree of g. Okay, so it's very interesting because it's basically saying if x and y are both Sn's, then the degree is enough to classify the maps up to homotopy. Okay, so actually it can prove even more than that. Moreover, if x is a compact, oriented, and connected manifold, of course without boundary, and you take maps from x to Sn, then the same statement is true. So f is homotopic to g if and only if the degree of f is equal to the degree of g. Okay, so we're going to prove this theorem next week, I think, or the following week, pretty soon. And the other thing I should say is that this whole index theory has a mod 2 version, which we'll actually talk about next time. But I didn't want to start with that and kind of redo everything. But so the intersection theory has a mod 2 version, which is basically, you know, you don't orient anything, you don't assume anything is oriented, but you assume everything else. So you assume compactness. So for example, you have x, y, and w manifolds that are not necessarily oriented, still with no boundary. And then you still have the dimension condition. And now, if you have a function from x to y, you can define sort of the mod 2 intersection number between f and w. And that's just going to be the number of points in the preimage of w. I guess you have to assume x is compact and w is closed. Okay, but the thing is, you don't assume orientability anymore, then the preimage is just a bunch of points and you don't know anything about orientability. So you can still define an intersection number, but now it's an intersection number mod 2. You just count the points and you don't put signs. And the point is that everything is still going to work because to prove like the fact that you have homotopy invariance, remember what we did is if we had a homotopy between two functions, then you look at sort of the preimage of the of the regular value by the homotopy, and you get a one manifold, a compact one manifold. And if you're in the orientable world, then the compact one manifold has a boundary which is it's an even number of points which have opposite signs. So I have the same number of points with a plus and the same number of points with a minus. But if you don't have any orientability, you don't have these signs, but you still have an even number of points. So mod 2, you still have 0 points. So that's why the theory works over mod 2. Okay? So I think that, I don't need to prove that, but I actually just want to say that the Hop theorem really is a theorem about degrees with signs. So, with index 2, you can also talk about the mod 2 degree. So if you just now have a function from xn to yn, and x is compact and y is connected, but you don't have any you don't have orientability in general, then you can still talk about a degree 2, a mod 2 degree, and you of course still have the fact that the two homotopic functions will have the same degree mod 2, but there is no way that you can have anything like Hopf theorem, even for spheres. Okay, and to see that, just take that function, from S1 to S1, that's just f, that's just z to the n. And of course, the degree mod 2 here is just n mod 2, which will just tell you if n is even or if n is odd. So that's not gonna do it. That's not going to tell you, that's, of course, for different n's, these maps are not homotopic because the sign degrees are different. Okay, but the degree mod 2 seems kind of useless, or it seems really, really simple, but it'll be enough to prove a very nice theorem that we'll prove next time, which is called the Jordan-Brouwer theorem. So let me just state the Jordan-Brouwer theorem, so you can see how powerful even the degree. The mod 2 degree is. So the Jordan-Brouwer theorem says the following. It's basically the generalization of the Jordan curve theorem. So if let x be a compact, connected hypersurface, then basically x separates Rn into two pieces, in two connected components. One bounded connected component and one unbounded connected component. So then Rn minus x is equal to U1, this joint union with U2, where U1 and U2 are open, connected, and U1 is a compact hypersurface. It's a compact manifold with boundary equal to x, and U2 is unbounded. Okay, so it's kind of saying that maybe you've seen this kind of picture before. It cannot self-intersect. And this is a little misguided. Then if you take R2 minus this curve, then it has exactly two connected components. And one is compact and has a boundary given by this curve, and the other one is unbounded with the same boundary. Okay, and that's true in higher dimensions for any compact connected hypersurface. Okay, so this theorem seems really hard, and it actually it looks really interesting and kind of hard, but it turns out that the proof is pretty straightforward, kind of just applying the degree mod 2 theory. And the specialization of degree is called winding numbers. Okay, so yeah, I think I'm going to stop here today. We have covered already a lot of material this week, so We'll continue next week.